Hello everyone. In this video we'll be talking about Gibbs free energy, which is symbolized by the letter G in thermodynamics. And the reason we call it Gibbs free energy is because the calculations that went into the concept of free energy were first compiled by a scientist by the name of Josiah Gibbs, and so we name the concept of free energy after him, and we give the symbol of free energy the letter G in honor of him. And Josiah Gibbs essentially is the father of chemical thermodynamics. So we owe a lot of our current understanding of and calculations of thermodynamics and chemistry, we owe that to Josiah Gibbs. And so he stated in his findings that free energy is the energy generated by a chemical reaction which is available to do work. So essentially, a chemical reaction will generate a certain amount of energy over its course. And that energy that it creates is available to be used in other ways. It can allow another reaction to take place, or it can jumpstart a reaction in another situation. And so Gibbs free energy is actually just as important in biology as it is in chemistry. So if some of you out there are more biologically minded and are more into biology than chemistry, this might be of interest to you, because when you think about the molecule ATP, adenosine triphosphate, we often hear in biology, whether intrabiology or other biologies, that adenosine triphosphate is used by our bodies, by our cells, for energy. It's produced to use as energy throughout our body. But where does the energy from ATP come from? We know ATP is involved with energy somehow. Well, it just so happens that it's directly related to Gibbs free energy. The hydrolysis of the ATP molecule involves giving off of free energy. When you split apart ATP, you generate free energy through that reaction. And that energy that's produced from that reaction is what's used as energy in our bodies. So, this is a little application for you. So delta G is definitely important stuff. But we'll be looking at it specifically from the chemistry side of things. And so, to use numbers with delta G, you can of course find values for delta G in tables that have been compiled and tabulated, and you can calculate delta G for a reaction the same old-fashioned way that we did for enthalpy and for entropy, where you can look up values in a table and you can take the sum of the products minus the sum of the reactants, and that will give you your delta G value for your reaction. But delta G also can be calculated using a unified equation of thermodynamics, where this equation will unify our three main state functions and temperature. So that unified equation is going to look like this, where we have delta G being equal to delta H minus temperature times delta S. And so as you can see, this equation unifies Gibbs free energy, enthalpy, and entropy, as well as bringing in temperature. And this equation is useful when we have a constant temperature. And we'll see that we use the value of delta G as a way to judge spontaneity of a reaction. So we could use a combination of enthalpy and entropy to judge the spontaneity of a reaction, but it depended on whether you have high temperature or low temperature, whether your temperature is equal, whatever. But delta G sort of has the final say on spontaneity. When your delta G is negative, your reaction is spontaneous. When your delta G is greater than 0, when it's positive, it's non-spontaneous. And when delta G is equal to 0, we have a situation of equilibrium. So delta G sort of has the final say when it comes to thermodynamics, which is why I like it so much. And this unified equation of Gibbs free energy is my favorite equation in all of chemistry. It is simply beautiful how it ties everything together. So what we can do now is we can look at calculating the standard delta G prime, which is taken at standard conditions. And we can look at how we can calculate for a particular reaction. So what we'll do is we'll take the reaction we looked at in the previous video, which was for entropy. So in the previous video we dealt with calculating the entropy of the reaction, and we're going to be looking at this reaction. So we'll have the reaction 2SO3 gas forming oxygen plus 2 sulfur dioxides. And if you remember in the previous video, we calculated the change in entropy for this reaction, which is shown below as 187.94 joules per mole Kelvin. And off screen, sort of by magic, I calculated the delta H for this reaction using figures I looked up on an online table. And so if you're a little squirrely on enthalpy and how to calculate that, I recommend going back and looking at the video on enthalpy and how to calculate enthalpy of a reaction. But it's literally the same way we calculated the entropy. And then our temperature, so we're going to do this at room temperature, which is, sorry about that, 25 degrees C. But we're going to need to do some changes here. So our units need to match. We need to have some units that work for us. So if you'll notice that the entropy is in joules, well, we need that to be in kilojoules, because we want to represent our delta G value in kilojoules. So these joules need to be changed into kilojoules. So if you remember, there are 1,000 joules in 1 kilojoule. So we'll divide this number by 1,000, and you'll get 0.18794. kilojoules per mole Kelvin. And that'll get you that. Then our temperature. So our temperature needs to be in Kelvin so it can cancel this K up here. We don't want this K in our final units. So we need to convert our temperature into Kelvin in order to cancel that K out. So we'll simply add 273 to this number, and it will be 298 K. And this is something I would probably just keep in mind anyway. It's pretty easy to remember. Whenever you see 25 degrees C, I would immediately write down next to it 298 K, because 298 K is what we consider to be SI units for standard temperature. So I would always try to keep that in mind. So now if we want to calculate delta G using these numbers, what we can then do is start plugging things into our unified equation up here. So what we're after is delta G, and so we'll start plugging in. So our delta H is 196.78, and we'll subtract temperature, which is 298, times delta S, entropy, which in kilojoules, and it's very important that you convert this into kilojoules. I cannot stress that enough. Okay? And if you want, you can go ahead and do this calculation off camera on your calculator. You should end up with, as your answer, is 140.77. And don't forget your units. Kilojoules per mole. So this will be your final answer. So how do we judge this? So you'll notice that our delta G that we calculated for this reaction is positive. If you have a delta G greater than 0, we're looking at a non-spontaneous reaction. So I will write those relationships below. So if your reaction is, or if your reaction has a delta G greater than 0, you have a non-spontaneous reaction. If your delta G is equal to 0, so if your delta G winds up equaling 0, we have a case of chemical equilibrium, which delta G and equilibrium have a very interesting relationship with one another. And finally, if your delta G is less than 0, so if your delta G is negative, we have a spontaneous reaction. So like I said, delta G often has the final word on what is spontaneous and what isn't. And so in this case, you'll notice that we have a positive value for delta G, which means that our delta G is showing us that the reaction is non-spontaneous. It will not happen on its own, which is very important. So there you go. This is how you use enthalpy and entropy to calculate delta G at a constant temperature.